Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is tensile membrane structures and CFD wind load simulation. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you may have. He's a technical support engineer also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide it with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, I want to give a brief overview of the primary structure that I've already modeled in our finite element analysis program, RFEM. So for the sake of time, I went ahead and modeled that primary structure, but what we will be doing together is modeling the secondary structure, and this would include the tensile fabric membranes as well as the boundary cables. From here, we want to get into the general loading. This includes the pre-stress forces that are necessary for the form finding process, but also a couple of simple load cases such as dead load and snow load. Then we'll move on to wind loading, and for this we want to utilize one of our newer programs, RWIND Simulation. So this is a CFD wind analysis program, which stands for Computational Fluid Dynamics. What this will allow us to do is to essentially take our structure into a numerical wind tunnel. We can determine what the wind pressures are. We can bring these back into RFEM as loads, and then we can integrate them with the other load cases. From here, we can utilize some of our other add-on modules, such as RF stability and RF-STEEL AISC, to design the supporting structure. And finally, I want to take a look at the influence on wind loads when we're considering additional structures or additional bodies in addition to our tent type structure today. So what we can do is to get started within our main program, RFEM. So as I mentioned, you can see here that I have went ahead, taken the liberty to model a few of our elements. If I turn off my grid, I'll quickly explain what's exactly going on here. Over on the left, we have a single standalone column, and I've modeled this at a slight incline. The member type is truss, so we have released the moments at the member start and member end. It is just an HSS member. The material is steel A500. Then we can take a look at our additional frames here within the model. So we have this center frame, which includes an arch beam at the top. We also have the frame on the right, which again is at a slight angle. When we look at these are just typical beam type elements. Again, those HSS sections, steel A500. What else we have in the model, which is a little bit difficult for you guys to see, are cable elements. So if I turn this into a wireframe view, you might be able to see those a little bit better with this orange color. So these cable elements are going to be required to essentially hold up these frames before we have even applied the membrane, fabric membranes to the structure. And this is true for out in the field as well. They provide stability for our columns and our center frames here. If I double click on one of these elements, you'll see that the member type is set to cable. I've defined them as 5/8 inch diameter, and I've also applied my own user-defined cable materials. So if you don't see the applicable cable material within the program RFEM, then you can always create your own user-defined, and this is the information that should come directly from the manufacturer. So once we have modeled this starting structure, I think it's important to make sure that we run a simple load case. And in this case, we'll run dead load or self-weight, just to make sure that the structure is able to stand up on its own and it does have stability. So again, this is all before applying those fabric membranes to the top of this tent structure. We can go in here to our load cases and combinations. And you'll notice that I have already created the first load case, and we can call this dead load. The self weight is activated as -1 in the Z direction. So once we have applied this self-weight load case, we can run the calculation, which I've already done so within this saved model, and we're presented with our global deformations. So the fact that the model has solved is certainly a good starting point. We know that there is stability within the main structure here. Now, of course, when we're looking at the sag displacements here for our cable elements, this certainly isn't ideal, but we'll go ahead and address those a little bit later on in the presentation. But essentially, like I said, we wanted to make sure that we had stability here for the main structure. So to begin modeling the fabric membranes and the boundary cable elements, I'm going to start off by selecting this node at the bottom of my frame column. And I'm going to use my Move Copy tool, which we can find up here within our toolbar. We're going to create one copy, and then we simply apply the displacement vector. In this case, it will be negative 6.5 feet, negative 15.75 feet, and 8 feet. I click OK, and now you can see this arbitrary node kind of created in between those two frames. I'm going to draw a new line element, and a line element is exactly as it sounds. It's not necessarily a member, it's not a surface, it's just a simple line element defining some additional boundaries here. So I'm going to snap to that node that I just created, and we'll snap up to the top of our frame. On the right hand side, we can right click to exit these dialog boxes, so just a simple triangular shape shown here. I'm going to take that newly created node and use the Move Copy tool once again. To create one copy, my displacement vector this time in the X direction is going to be negative 3, 0 in the Y, and in the Z it will be negative 8. The purpose for this node is we want to eventually create those fabric membranes here, but we need to anchor them down to the ground. So we can use our line element once again, and we'll connect from our first created node to our second created node. We right click, and we have that simple short line segment here. In a similar manner, I'm going to take the node at the bottom of my standalone column, use the Move Copy tool, create one copy, and my displacement vector here will be negative 24.25, 0, and 8. I click OK, and again, we have this arbitrary node kind of in between that column and that frame. So using a new line element, we're going to connect the top of the column down to this node and back up to the frame on the right. Just like what we did before, we'll take this newly created node here. We'll use the Move Copy tool, and we want to create our anchor cable. So we'll select one copy. The displacement vector will be negative 3, 3, and negative 8. I click OK. And finally, we draw a line element connecting from the membrane up here down to the bottom, the ground. Okay, so currently these are just typical line elements as we mentioned. What I can do is to highlight to select them, hold down my Control key, select the adjacent 3, and I'm going to double click on these line elements. We have the ability under this second tab to assign a cross-section and material to the line to convert it into a member. So I'm going to do that here, but instead of a typical beam type member, I'm going to create a new cable element. Now, typically I could create this cable element, assign a new cross-section, maybe a new material, but I've already have cable elements defined within the model, and I want to use this same diameter, this same material, so I can simply select it from my drop-down box here. I click OK. Program asked me to clear the results, that's fine, and now you can see the member information is given to me within this dialog box, and these lines are now orange to indicate that they are cable elements. We'll take these same 6 cable elements, we'll highlight them holding down our Control key, and we're going to take advantage of our mirror tool. The mirror tool can be found up here in the toolbar. What this allows me to do is to create a copy by mirroring about the YZ plane, and I can select the point to mirror about. And for this, we can just choose any point that's at the center of this structure, and we could choose the top of the center column, for example. You'll notice the coordinates are automatically populated for me here. And now you can see rather than having to redefine that geometry on the other side, we simply have copied over those cable elements to the other side by just using that mirror tool. Now, the final thing to do with these boundary cables is to apply supports to the bottom of them. You'll notice that the rest of the structure has nodal supports applied. And if I take a look at these, the type of support here is just a typical pin. You can see that I have fixed translation in the X, Y, and Z, but I have released the moment about X, Y, and Z. So sticking with the same methodology, what I can do then is to apply that same nodal support to the bottom of these anchoring cables. So I can go up to my tools and choose new nodal support. Now I don't need to redefine that particular definition type because again, we already have it available to us within our model. So I can use my drop-down box here to select the type of support, my pin support. I click OK, and then I can just simply click on the bottom node of those anchoring cables. And now we have all the supports applied. So this really finalizes the cable elements, and what we'd like to move on to next are the fabric membranes. And the fabric membranes will be created with surfaces, 2D surfaces within the program. Now the problem with all of our surfaces that are available here within our drop-down is this makes the assumption that the surface will be in a single plane. And for our complex structure today, the surfaces certainly won't be in a single plane. So what we can use instead is a couple tools down. We want to apply a new quadrangle. And a quadrangle does not require the surface to be in a single plane, and we'll see this as we begin to model here. Now we want to define a new material for our membrane. So we'll select a new material. We can give it a description here, a membrane. The material model will be selected from my drop-down box here as orthotropic elastic 2D. What orthotropic allows us to do is to define two different stiffnesses in both the X and the Y direction. Now, this information should come directly from the manufacturer for whatever type of fabric material that you're using. So for today, let's say that we've referred to our manufacturer and he's given us the stiffness in the X direction as 1 gigapascal. But notice that my units here are KSI. So just a nice little trick within the program. If you don't want to manually convert gigapascal to KSI, what I can do here is type in 1.0. Then I can manually type in capital G, capital P, lowercase a for gigapascals. Notice when I click in the next cell, the stiffness is automatically converted to KSI, 145.04. We can do the same thing in the Y direction. So the stiffness from the manufacturer is given to me as 0.8 gigapascals once again. I click into my next cell, it's 116.03 KSI. Now, as far as this shear modulus, this is the shear stiffness perpendicular to the plane. So when we're looking at the local YZ and local XZ of these surfaces, we really don't want much stiffness at all. But the program does not allow us to enter in 0 here, so rather we can just type in a very small number of 0.001. Same thing for the next shear stiffness in the XZ. And finally in the XY though, we do want some stiffness, again given from the manufacturer as 0.3 gigapascals converted to 43.51 KSI. Poisson's ratio will be set to 0.2. I click OK. The specific weight will be 64 pounds per cubic foot. The coefficient of thermal expansion can be left at 0. I'm not applying thermal loads to my model today, so this is irrelevant. The partial safety factor can be left at 1.0. The other feature that we can do is to change the color of our surfaces. So blue is the default here, but if I'd like to change the color maybe to something that's a little bit different than what we're seeing for our members elements here in the background, I can just choose a light green color. I click OK. And so now we have defined those material settings for my fabric membranes. We want to change the stiffness type to membrane orthotropic, and we'll go into the detail settings here. Under the second tab is where we'll set the thickness of the membranes at 0.04 inches, and I click OK. So now that we have defined the material as well as the stiffness properties, I can click OK, and now we're ready to begin to define the boundary lines of this surface. So for this, I'm going to orient my model in the plan view. So I'm going to choose in the reverse Z direction from my drop-down box here. So as you can see, we're just in a simple plan view. Then to define my first membrane, what I'm going to do is just to select the members, including the cable elements, that make up this first membrane. Now, once I close the loop here, you'll notice that we will get a dotted line, and that indicates my first membrane. We'll do the same thing at the front of the structure. We'll just go ahead and select each member in order, and once we close that loop, we should see a dotted line up at the front. So I can right-click to exit. Maybe I turn this back into an isometric view, and we go back into a rendered view, and we can see those fabric membranes applied to the structure. So certainly not in a single plane. That's the advantage of using that quadrangle feature. Now, everything that I have modeled so far has been completely straight lines. The cable elements are straight, our fabric membranes are straight lines, and realistically, we know once we apply this pre-stress that we're going to see biaxial curves for our fabric membranes. Our cables may have some catenary shape to them. So this is where we want to take advantage of one of the add-on modules that's available within RFEM that's called RF form finding. And this add-on module essentially allows us to define the predefined properties such as these pre-stress forces, cable sags, and so on, and it will find the deformed mesh for us before we continue on with the static analysis. So a simple way to explain this is the cable elements. They are completely straight. Form finding will allow us to define a cable sag, for example. We run the form finding process, and then the program will come up with the catenary shape for us. So to activate form finding, I will go to my project navigator and I right-click on the model name to access the general data. Under the Options tab, we have here RF form finding. So I just simply need to check this checkbox, and the program will activate this add-on module within my model. I click OK. Now, nothing has changed, but what we'll see in just a minute is the features that it has released within RFEM to allow us to run that form finding procedure. So I'm going to go to a plan view once again, and that's the reverse Z direction. I'm going to turn this into a wireframe view. And I'm going to select my two cables in the rear here by holding down my control key. So we can see they're highlighted in red. I'm going to double click them. And RF form finding has now given us the ability here to edit the member type. This previously was not available to us. We can define the cable target length, the sag, or the pre-stress force within the cable. For these two rear cables, I'm going to assign a pre-stress force here of 0.225 kips. So when I click OK, you can see that nothing has changed so far. We're just simply defining these pre-stress forces. What I do want to do is the exact same process for my front three cables as well as my two rear cables. Remember, this is all part of the primary supporting structure. I double click on these elements. I'm going to go into the detail settings here. Now for these ones, I'm going to assume that the pre-stress force I place in these cable elements spanning between my two frames will inevitably impact the rest of these cables for the supporting structure. So for these, I'm going to set the target length to 100%. As I've modeled them now, I don't want that length to change. And I can click OK. I'm going to move to my boundary cable elements on the exterior of the structure. So remember, these ones are useful for defining the boundary conditions of the fabric tensile membranes. I can double click on these. I'm going to edit them. And for the properties here, I will define a target cable relative sag of 10%. We can also refer to this picture over here on the right to kind of determine what the sag should be set to. I click OK. And finally, our last four cables would be the short anchoring cables that go ahead and attach the fabric membrane down to the ground. I'm going to double click on these. We're going to edit the detail settings here. and we're going to set a pre-stress force to something quite a bit higher at 6.75 kips. I click OK. So if we're curious to see visually those pre-stress loads defined, what I can do is to select RF form finding from my drop-down box here and turn on the display of my loads. So we can see how those pre-stress defined loads apply to each cable element. This is just a good way to check to make sure we didn't miss any of those cables. Now, similarly, we want to apply some pre-stress settings to our fabric membranes, of course. So for this, I'm going to select my two fabric membranes by holding down my Control key. I'll double click on them. Now we've already been within this dialog box before. Remember, we set the thickness of our membranes here. But what we did not see before was this form finding tab. And this allows us to define a pre-stress force or stress in the warp and weft direction, which is the X and Y axes of our fabric membrane. Now we will be applying a standard calculation method. The projection is more for conical type structures, so standard is more for flat elements. We do want to apply a pre-stress force, and we'll actually just keep this as the default of 0.07 kips per foot. And I can click OK. So once we've applied those pre-stress settings, what I can do is to go back into an isometric view. Let's turn off the display of our loads. Let's go back to a rendered view. And we want to have RF form finding selected from our drop-down box here. And I'm going to start the calculation by clicking on this Show Results button. So what the program's doing now is nothing more than just applying all of these predefined pre-stress forces from our cable elements as well as our fabric membranes to the structure, and then it's going to come up with the relevant shape for us. So we can see the initialization of the calculation method here, and we should see a progress bar as well, just kind of showing us the max displacement for every iteration. So after this iteration is complete, what we'll be presented with immediately in RFEM is the deflected shape. So now what you'll notice is that my FE mesh, which is displayed here, now has this curvature to us. Again, the cables have a catenary shape. The fabric membrane has biaxial curves. This would be the FE mesh that we would move forward with then for the additional static analysis. Now, before I do, I want to just explain a little bit about the results that we have available to us here. So under the Results tab, we can go ahead and collapse most of these trees, and we want to take a look at the surfaces tree, and in particular the shape for the contour lines. So we can compare this to our colored panel over here to see where we have higher contours versus lower contours. We can view inclinations. For example, we'd expect higher inclinations here where the fabric membrane is a little bit more vertical than our flat membrane up at the top. So just kind of a way to double check this form finding shape. Now, with that said, going back to the deflected shape here, and maybe we change our deformation factor to 1.0, I'm going to take a look at the elevation view. And the rear part of the structure looks fairly adequate for the curvature that I'm seeing, but the front part of the structure, I'd really like to see a little bit of a higher curvature here. So that's fine. We just need to manipulate maybe the pre-stress settings, but also I want to point out, if we go into an elevation view and maybe I turn off my results here, let me also turn off my FE mesh. I'm going to right click to turn on the local axis system of my membranes. So remember, for our membrane material that we got from the manufacturer, that the material is actually a bit stronger in the X direction versus the Y direction. So you can imagine that this is really important then for the placement of our local axes for these membranes and in which direction they span. Currently we have the X direction spanning parallel to our main frames here, and the Y direction is perpendicular. What I'd actually like to do is to rotate that. I want the Y direction to be parallel to these frames. So I can do so by selecting both of my membranes, double clicking them, and under the Axes tab, you can see that we have the ability to set the local Y-axis parallel to a line that I can choose within my model. And I can just choose either one of the frame beam elements, line number 8 here. I click OK. Through these dialog boxes, the program tells me it has to clear the results. And you'll notice now the y-axis is parallel to those frames, the x-axis is perpendicular. Now, in addition to this, what I'd also like to do is to go back to this General tab, and under the membrane settings and the form finding tab, I'm going to increase the pre-stress force in the y direction. So by manipulating the orientation of my x and y axes, I now have the ability to set a different force in the warp versus the weft direction. So in the y, we'll actually double this to 0.14 kips per feet, and we'll leave the x orientation the same. So I can click OK through these dialog boxes, and what I'd like to do again is to apply the RF form finding calculation again. And I've made no changes to my cable elements, so those should stay the same exactly how I had them defined before with the sag and cable length. We just modified the orientation of these surfaces as well as increase the predefined stress in the y direction. So once the program has solved for this new shape, again, will be presented here with our deflected shape in RFEM. I can go ahead and right click here to turn off the local axes of the system. We're currently looking at the deformation. We take a look in the elevation view, and we can change the deformation factor back to 1.0. You can see a nice curvature here in the front, so a little bit higher than what we were previously seeing before. The other thing to check are the surface internal forces. So for our NX forces, these would be the tension along the local x-axis, we should see about 0.07 kips per feet, because remember, this is a pre-stress force that we applied. And although it varies slightly, you can see that the average here is about 0.07 according to this color panel. In the NY direction, again, it varies a little bit, but as we'd expect, the average value is about 0.14 kips per foot. So just to compare the pre-stress force to what we're actually seeing after the form finding process, and everything looks good. So again, this is the new shape that we're going to move forward with for the additional static analysis. So the next load case that I'd like to run here is snow load. And I'm going to go up to my load cases and combinations. We're going to create a new load case here, and this one will be called snow load with the action category set to snow. I click OK, and I make sure that I have snow load selected in my drop-down box up at the top. We want to apply a new surface load, and we can do so within our toolbar. We have new surface load here. For the snow load, I'm going to apply this in the projected Z direction. So we might be wondering, well, what's the difference between the projected Z direction versus related to the true area? And with the projected, this will actually take into consideration the angle of my fabric membrane. So we'd expect with snow loads, the snow would probably slide off when we're looking at the edges here of our fabric membrane that are almost vertical. But up at the top, where we have a pretty flat area, we'd expect to see higher snow loads. So that's what the projected area allows us to do. The magnitude here is going to be fairly small, negative 0.006 kips per square foot. The reason for this, maybe we don't expect this tent or canopy to be operating during the winter, but we still want to account for some snow load. I click OK, and then it's really just as easy enough to select my two surfaces here. And now you can see the surface loads applied to the top here in the projected Z direction. We also can view a plan view, and I'm going to go to a wireframe view. Those same area loads have now also taken the shape of my new form finding mesh here. So we can run a quick analysis for snow load. Program, again, doesn't need to solve for the form finding shape. We already have that. It's just simply going to apply the snow load here in 5 load increments, and eventually we'll be presented with our results. I like to do this just to make sure that the load case that we've just applied makes sense with the deflected shape. We don't have any modeling inconsistencies. So once this is done solving, again, we'll be presented with our results here. Let's go back to an isometric view and let's take a look at the global deformations. And let's also view the deformation factor set to 1.0. So as we'd expect, we have higher deformations at the top here, where again, we're going to see more snow load accumulation rather than out here at the exterior where we have steeper angles. So everything looks okay there. All right, so the next thing to move on to are wind loads. And for this, we're going to utilize one of our new programs called RWIND Simulation, and this runs a computational fluid dynamic analysis. Essentially, what we're going to do is we're going to take this structure, we're going to integrate it within the standalone program RWIND, and we're going to put it inside of a numerical wind tunnel. Now, the purpose of the numerical wind tunnel, if we kind of relate this to the AISC E7, is that when we refer to the standard, not just the AISC E7, the NBC 2015, or any other, international standard, I think it's quite clear how to apply minimum design loads when it comes to basic rectangular buildings. Even dome structures, silos are pretty clear within the code. But when we're getting into these fabric membrane structures, and in particular these very unique geometries, it's incredibly difficult to determine what these minimum wind loads should be from the standards. So the hope is to use a program such as RWIND Simulation for a CFD analysis to better understand what these wind loads should be set to and how we can incorporate the new loads with our structure design. Now, by no means is RWIND meant to take the place of the standard. The code has not set the CFD analysis or numerical wind tunnel to an approved method quite yet. So rather, we just want to use it as a tool to check our wind loads. And that's what we'll be utilizing it for today. So in order to access RWIND Simulation, we want to launch the interface here. We can do so under Calculate, and we select RWIND Simulation. You can see this dialog box is brought up here. And I also want to preface that I've done a previous webinar a few months ago, completely devoted to RWIND. And it really went into the details of the theory. I went over all of these different settings and properties that we just simply don't have time for today. So we'll kind of breeze through it today. But if you're more interested in kind of like I said, the details of this standalone program, how we integrate it with RFEM, you can refer to our YouTube channel or our website to view that recorded webinar. So the first thing to define here are the wind directions, and you can set a step. For example, you can see the default here is 45 degrees. Well, the program will then run different load cases here for the wind direction coming at 0 degrees, 45 degrees, 90 degrees. Now, this is all relevant to the global x-axis of our model. So for today, I'm going to choose 90 degrees. And keep in mind, though, that our structure is symmetric about one of its axes. So rather than kind of wasting my time, so to speak, doing two wind load cases where I'll see the exact same results, what I can do here is to select the manually defined directions, and I'll delete 180 degrees because that's the same thing as 0 degrees in my case. The second section here is the wind velocity profile. And you can see from the drop-down box here, I have a couple of standards available to me, including the Eurocode. I also have the AISC E7. And I'm also pleased to let you know that within the next release, we'll have the NBC 2015 available here. What this does is it will integrate the standard and some of these factors that we're seeing here to generate this wind velocity profile. This wind velocity profile is given to us in miles per hour as a function of height over the height of our structure. So we're going to choose exposure category B, and the factors here, topographic factor, wind directionality factor, ground elevation factor, gust effect factor, these all come from the standard. The default here is 1.0, so as the user you would want to modify these based on your project, where it's located, and so on. So we'll leave these as default today. The basic wind speed. So this comes from the AISC 7 wind load maps. And for this, what I'm going to do is to access the Dlubal website. Under solutions, we have what's called the GeoZone tool, and you can see that here. We have incorporated many different standards, including the AISC 7. You'll see here the NBC 2015, as well as many other international standards. We've taken those maps for snow load, wind, tornado, seismics. We've integrated them with Google Maps technology so that you have the ability just to type in the address of your project location in order to pull that information directly from those standards. So just a little bit more helpful rather than having to manually flip through those tables within the code. For today, we're setting the risk category to 1. We're using the AISC 7. We're selecting the wind load here. And let's say my project for today is located in Sacramento. So I can type in Sacramento, California. You can see that a pin is dropped here with the location. And my basic wind velocity is given at 90 miles per hour. So this would be the information back in RFEM that I would want to input here for the basic wind speed. And you can see my wind velocity profiles automatically updated. So this is the wind speed that is entering the numeric wind tunnel. Now, in turn, we don't have to use a standard. We can select user defined here. We can import and export from Microsoft Excel, or you can manipulate these values that were already created. So that is an option if you don't want to use the predefined standard. The load cases tab, you can see here we have 0 degrees, 90 degrees, 270 degrees. These are the 3 load cases that will eventually be generated within RFEM that I can combine with my additional load cases such as snow load, dead load, live load, so on. The settings tab, in particular, let's talk about the flow parameters, the density and kinematic viscosity. These are just going to control the air properties that are flowing within the numerical wind tunnel. The calculation parameters here, this is for the density of the mesh within the wind tunnel. The level of detail here is for the shrink wrap mesh that will encompass our structure. The higher the level of detail, the higher the percentage here for the density of mesh. Sure, the more accurate your analysis is going to be, but keep in mind the longer your calculation time will also be. So there's kind of a happy medium here to make sure that your results aren't changing too much when you increase these values, but you're not waiting hours and hours for the calculation to solve when it's really not making much of a difference. The load case to be generated will start at load case number 3. That's just, remember, we have dead load as load case number 1. Load case number 2 is snow load, so load case 3 will be our first wind load. We have some turbulence and turbulence intensity settings over here on the right. The member load distribution, these will be brought in from RWIND as concentrated loads. We also have the ability to define uniform or trapezoidal loads instead. Again, this will make sense when I actually show you these loads shown graphically later on. So under the load cases tab, we have the option to calculate all in the background. You'll just simply see a progress bar pop up, and essentially our RWIND simulation will never be open. Everything is calculated underneath the hood. We'll see checkboxes here once they're calculated, and the loads will automatically be available to us within the main program RFEM. Now in turn, we can choose any one of these load cases and open an RWIND simulation. So what I have done, because it does take just a minute to solve, is go ahead and solve for one of these particular wind load cases, and I've chosen the 270 degree. I wanted the wind to flow in this numerical wind tunnel, which you can see here, from left to right through this large opening. So as I mentioned, the RFEM model is completely exported into this numerical wind tunnel. We even have the curvature here from the form finding process. So everything is accurately represented. The wind tunnel mesh out near the edges, it's pretty coarse, but as we move closer to the model, you can see that it's more refined here. So that's kind of what some of those settings that I showed you will control. So when we run the analysis under this simulation tab, what will be presented with here, and this will take just a few minutes to run, so that's why I pulled up this already saved model. You'll see the surface pressure. And the surface pressure, if I zoom in here and I hover over my mouse, will show me that, of course, the highest pressure I'm seeing is up here on that front frame as we see the wind loads move from left to right. We're also seeing some high pressures here as our tent kind of increases in height. On the back side, we're actually seeing negative pressures. This means that there's uplift occurring, which kind of makes sense. We're going to see the wind loads pass underneath this structure and push up on the back side of the fabric membrane. So we'll get back to this in just a minute, but I do want to display the pressure field here. And the pressure field is my second option where I can view the wind pressures around the model. So it does take just a second to populate here, but you can see that we can eventually view the pressure field, but not only that, we can actually slide this around the structure to see the pressure updated in real time. The show reduced domain checkbox here, if I uncheck this, we're now seeing pressures for the entire wind tunnel. This probably isn't of interest to us, seeing pressures way out here, so that's why by default we have this show reduced domain option. So we'll reactivate that here, and the next thing I want to show you is the velocity field. In a similar manner, we're going to see the wind velocities around the structure in feet per second. Again, I can slide this, I can change the planes of this velocity field, can kind of see these velocities at the back of the structure that were causing that uplift. The velocity vectors, if we turn this to somewhat of an elevation view, it might be of interest to us because what we're viewing here is not only the magnitude of the velocity in feet per second, but also the direction. So again, seeing that uplift pressure in the back caused by these velocity vectors here. We also see the velocity passing over the structure and through. And probably everyone's favorite would be the streamlines. And the streamlines takes just a minute to populate here, but it's going to show the direction and the magnitude of the wind loads. So let me zoom out here so you can get a better look, but you can see these streamline particles kind of passing again around the structure and see the exact path that they're going to take. We can also activate this streamline animation. So again, just viewing how those wind particles passing over through the structure and kind of circulating in the back here. So I will get back to some of these animations as well as different views for our results a little bit later on. But the most important thing to remember from this analysis is the surface pressures. This is what we want to get from RWIND simulation on our structure. So going back to RFEM then, what will automatically happen, and I'm going to cancel out of this dialog box and jump to an already saved model. Again, it takes about, 10 minutes or so to solve for these three different load cases. We will see under our load cases and combinations 3 new load cases generated, including 0 degrees, 90 degrees, and 270 degrees. So maybe you want to select all 3 of these. You would redefine them as wind load, and that will just tell the program, okay, let's incorporate these into my ASCE7 wind load combination, or to my ASCE7 load combinations. The Actions tab here, you can see we have a dead load, snow load, but also wind load. And this is important because we now have 3 cases under wind load, and we want them to act alternatively. We don't want them to act at the same time. So the program has already assumed that. It will set them to alternatively. We shouldn't see 2 of the wind load cases acting together. The combination expressions is my ASD load combinations as well as my LRFD load combinations generated from the ASCE 7. So LRFD is listed first, but second I have my ASD load combinations. I've actually unchecked this used checkbox. I'm not really so interested in checking deflections for today, so we'll just keep this simple with only LRFD load combinations. Under the load combinations tab, this is where we can see all of those LRFD load combinations individually listed out with dead load, snow load, and wind load. Notice under the calculation parameters, everything is run according to a large deformation analysis. This is required because we have cable elements and these fabric membrane structures within the model. We don't even have the option, because they're grayed out, for a geometrically linear analysis or a second order analysis. It does have to be run according to a third order analysis when those elements are defined. So, what I'm going to do is to jump back to the RFEM model and let's view our results for the wind load case. And the first thing that I would like to show you here is the actual applied loads that we're bringing in from RWIND. Under the Views tab, we can activate our members by type, and I'll choose only my beam and truss members here. And I'm going to turn on my loads for 270 degrees. So you can see that at every FE mesh point, I have point loads in the X, Y, and Z direction. This is the loading information that's brought in from those surface pressures within RWIND Simulation. Now, this is being applied at every FE mesh point within the model. So what I'll do here is to deactivate this view so you can actually see what's going on. And it's a little bit overwhelming. We have many FE mesh points here at the fabric membrane. So at every one of these FE mesh points, X, Y, and Z loads are being applied. Again, completely overwhelming. So we'll just go ahead and turn off this view of the loads. Rather, let's take a look at the results once we run the load case. And I've already done so again. I've saved the results. We're first going to view our global deformations here. And the global deformations will give us a better understanding, which we can see in the backside of the structure, that uplift occurring. We have pressure towards the front membrane here, exactly as we would expect when wind is flowing from left to right. Now, I mentioned that the view of the loads is a little bit overwhelming, so how can we be sure that the correct loads were applied to the structure? Well, what's beneficial here, if I collapse some of these trees, is to take a look at the distribution of the load. So I can view this for the global X direction, which, okay, I'm viewing the distribution of the load in kips per square foot for this particular wind load case, but also in the Y direction. So this is going to make the most sense. We can see pressure acting towards the membrane up at the front of the structure, and in the rear we're going to have positive values for uplift or tension forces, essentially away from those the fabric membrane in the rear. So instead of displaying the loads, we can solve and take a look at the distribution of the load instead. Now, as I mentioned, we want to incorporate these wind loads with the rest of our load cases, such as dead load, snow load, and let's take a look at load combination number 5 here, which includes dead load, snow load, and this same wind load. Once we solve for it, we can take a look at our deformations, and everything kind of acts as it should. Notice we have some additional deformation in the vertical direction due to those snow loads and some for the self-weight. What I'd like to check here under these surfaces are these NX and NY forces. So we're currently viewing NX forces in kips per foot. So these are the tension forces within the membrane. This is certainly something that we want to compare to the capacity of the fabric membranes themselves to make sure that they're not going to fail or tear or anything of the sort. This is, again, information that we'd want to compare to what we're given from the manufacturer. Same thing for NY. These would be the tension forces in the local Y direction of the membrane, and we can get all this information here graphically as well as within the tables. In addition to the surfaces, we probably want to take a look at our supporting members. So we can expand our members tree, and maybe we want to view the axial forces. And I'll turn this into a wireframe view here. We're going to see axial forces or normal forces within our cable elements, within our frame members. Again, this is information that we need to make sure that these cables aren't going to fail. For our frame members, we can also view shear forces in the weak and strong axis direction, as you can see here, bending in the strong and weak axis direction as well. So this is the information then we'd want to use to design the supporting structure. Now, the huge benefit of RFEM, of course, is that we have not only run the form finding process, so all of those internal forces generated from the form finding pre-stress forces are transferred to the supporting structure. We've incorporated it with RWIND for the wind loads. And finally, we can also design the supporting structure all within the same program with some additional add-on modules. So that's what we'll move on to for this example. I'm going to turn this back to a rendered view here, and let's take a look at, and actually let me keep this in wireframe view. Let's take a look at our first add-on module called RF Stability. So I can launch RF Stability from my project navigator over on the left-hand side, and this add-on module will essentially allow me to run an eigenvalue analysis and determine the corresponding buckling mode shape. So it's very, very powerful in what it can do. The number of eigenvalues that we can solve for is set within this first option. Now, the default is 4. Maybe we set this to 6, for example, today. You can solve 100 eigenvalues if you'd like. But keep in mind, the higher number the eigenvalue, the less likely that we're going to see buckling modes that will really ever occur, because the critical buckling load factor will be so high. And I'll explain that in just a minute. But really, we're probably most interested in these lower eigenvalues. We want to import in the axial forces from either a load case or a load combination. Now for today, I'm most interested in the buckling behavior of my columns within my frame. And for this, I want to import in a load combination that creates the highest gravity loads or the normal forces within those columns. So we'll select load combination 2 here that includes both dead load and snow load. So I'm going to begin the calculation here and just also explain that these internal forces that are being brought in, they are nonlinear. We are including the form finding process, those cable elements. We are running a linear eigenvalue analysis, which we can see over here on the right hand side. We do have the ability to run a nonlinear analysis. So this may be suggested if our critical load factor is less than 10. We'd want to run a nonlinear analysis, or if we're just simply looking for a little bit more accurate results when it comes to including geometric and material nonlinearities within our model. Now for today, we're just looking for the general buckling behavior of the structure. So there really is no need to get a super detailed analysis, and you might often find that a nonlinear versus a linear isn't that much different. Eventually, we are presented with our results, and we have 6 different eigenmodes listed here within our results table, along with a critical load factor for each one of them. So this critical load factor is the factor that you can multiply load combination 2 by before you're going to see the relevant buckling modes shown in the background here. This is why if you have a critical load factor less than 10, let's say, maybe it would be suggested then to move to a nonlinear analysis, just to make sure that buckling isn't a concern for your structure. Now, if you're seeing critical load factors less than 1.0, this is a huge problem. This means that we can't even apply 100% of the loads from load combination 2 before our structure is buckling. And quite honestly, you would not be able to solve an RFEM because the program would flag you that you're exceeding the critical buckling load value or the capacity. So we could use RF stability to determine where our problem could be. So again, these critical load factors are listed here. The lower the critical load factor, probably the more of a concern it should be for that particular buckling mode. The program is synced up in the background so I can view these different eigenmodes and the behavior of my structure, or we can choose this graphics option here. And I'm technically still within the RF stability add-on module. We can see this from my drop-down box here. But this gives me the ability to view these different buckling mode shapes. And we can see from the first buckling mode shape, we kind of, if we turn off here our isobands, we can see the entire structure is kind of racking off to the right. Our second buckling mode shape would be buckling of our column elements here. We have our third buckling mode, just a reversal of the orientation. And the fourth buckling mode shape, it looks like the columns are kind of buckling inwards here. So quite powerful in just understanding, again, the behavior of the structure. So going back to RF stability, the other thing that I want to point out on top of the critical load factor are some of the other information and tables that are available to us. More importantly, under the effective lengths and critical loads. Notice for each member here, we have 6 different eigenvectors. And the effective length factors are also given to us for each member. So this is important if you're designing per the effective length method from Appendix 7 within the AISC standard. We want to input in a correct effective length factor for the AISC design, and generally these are given to us from the general tables for pin fix, condition, but the program here is giving you the true effective length factor for the strong and weak axis based on this buckling mode. So can be pretty powerful, and I'll show you in just a minute how we can incorporate this with our RF-STEEL AISC add-on module. Okay, so the stability design we have generally covered, and now, as I mentioned, I want to move on to the steel design for these frame members. For this, we can launch RF-STEEL AISC. Again, I've done previous webinars devoted entirely to just these steel modules, so refer to them if you're looking for a little bit more detail than what we can give today. I also want to let you know that the RF-STEEL CSA module for Canadian steel design, same workflow that you're going to follow what I'm showing you today. We choose the design according to the LRFD 2016. Then we want to choose the members that we would like to design. So what I'm going to do here is to turn this back to a rendered view. We'll go to our Views tab, and we will activate the members by type for only our cable and truss members. So I've selected members 1 through 9 graphically to design here. We will choose all of our LRFD load combinations for the ultimate limit state design. Now, serviceability, I'm not, again, considering any deflection design considerations today, but normally we would move our ASD load combinations off to the right here. Then I can just simply move down my list. So I have my materials, which were automatically brought in from RFEM as steel A500 for these members. Same thing for the cross sections. We have HSS members, all the cross section properties shown to us here. Intermediate lateral restraints. This is if we had any top or bottom flange bracing, and this would affect our lateral torsional buckling calculations. Now in our scenario today, we have no intermediate lateral restraints. Sure, we have this fabric framing into these frame members in the intermediate or the lateral direction, but it's certainly not going to provide any support from lateral torsional buckling. So we'll leave all of this as empty. The effective length. So this is strong axis buckling, weak axis buckling, flexural torsional buckling, and lateral torsional buckling. So as I mentioned from RF stability, if we are designing per the effective length method from Appendix 7, then we would want to input in here the effective length factors for our strong axis and our weak axis. Now what the program allows us to do is to integrate with RF stability. So we can set the input for all members here, and we can choose the effective length factor for the strong axis. I select my 3 buttons here, and again, these tables should look pretty familiar. This is what we would find within the AISC standard, but instead, I'm going to import in from RF stability my first buckling mode shape, the effective length factor for the strong axis. I'm going to do the exact same thing for my weak axis here. So when I click OK, notice all of these K factors were automatically updated according to that first buckling mode shape from RF stability. So pretty powerful in the sense of what we can do here. Now, in turn, if we are designing per the direct analysis method from Chapter C, the code does tell us that we can set this to 1.0 for the factors, so we can just go ahead and overwrite these again and set them back to the default of 1.0. Just to quickly preface as well, if we are designing per the direct analysis method, back in RFEM, we'll want to reduce our stiffness for our members, and I can quickly show you this here. If we go back to RFEM, I double click on my members. We have here the modify stiffness. This is going to apply a tau sub B stiffness reduction as well as the multiplication factor 0.8 to our flexural and axial stiffness. Again, this is just required per the standard, Chapter C, when we are designing per the direct analysis method. Those previous webinars that I mentioned really give quite a bit more information on the background of that. So just briefly touching on that. So we're ready to run the calculation here, and we should see the module solve pretty quickly. We already have all of the internal forces being brought into this add-on module. All that we're doing is applying those different AISC equations to eventually get a design ratio. And we can view design by member, for example. And if I kind of pull this down, notice that the program is once again synced up with this table to point me to exactly which member I'm looking at. That big red arrow is going to be the controlling internal force for that particular code check. For each member, we're also giving you all of the code checks from each chapter. So chapter F, G, E, H. In addition to that, if we expand out some of these settings, we're trying to give you as much information as possible in terms of how the member is classified, non-slender, slender, compact, non-compact, as well as all of the variables, the code references that go into that particular design check. So pretty transparent. Now, ultimately, we're getting a max design ratio of 0.59 for all of my members considered. I'd say that's quite good for our design today. The last table here, we have the parts list by member. So this is a material takeoff. We can view the total length here. We can view the total weight. We can export this information to Microsoft Excel. So that may also be helpful for us. And finally, we can view this information graphically as well. So technically still within the RF-STEEL AISC, which we can see from our drop-down box. I'm just viewing my ultimate limit state design ratio graphically, so we can kind of see where those higher design ratios can be found along these frame members in that standalone column. So that really encompasses the entire design process for this fabric structure, including the supporting structure for our steel members. The final thing that I want to cover, which will just take a couple of minutes, is the influence of additional structural bodies or structures in general and how that plays a role with our wind loads. So let's assume, for example, our structure today is, again, some type of tent covering structure here, and we want to use it to cover a seating area. So I'm interested if I place that seating area underneath my tent or my canopy here, how will that impact my wind loads? Because it could be pretty significant. Under a saved model here, I have modeled the stair structure that will be placed underneath the tent. Now, I'm not interested in designing these stairs. I simply created this model for the geometry purposes only. So they're created with surface elements, the thickness, the material, it doesn't matter. I just simply have input in the geometry, which is the most important part. If we take a look at the dimensions of these stairs, it's quite large. So the length here is 62 feet. And then if we take a look at the height, measuring from the bottom of the structure up to the top of the rail, 17.4 feet. So pretty large structure to be placed underneath the tent. What I'm going to do is go to File, Export. I'm going to use this option over on the right to export the RFEM data for RWIND Simulation as a .vdp file. So when I do this, this allows me to save this file to wherever, my desktop. I'm going to go back to my original structure here, and I'm going to open up RWIND Simulation. So this same interface will populate here that we previously saw where we put in all of our RWIND settings, and it's taking just a minute to populate here, so we'll just give it just a second. But essentially what we're hoping to do is to incorporate the two models together within RWIND. So under the load cases, what we can do for wind in the 270-degree direction. We want to open an RWIND simulation for this particular case. And the program will launch RWIND simulation. And actually, let me try that again. Open an RWIND simulation. We're going to export this tent structure. Nothing that we haven't seen before. But this time, under the model tree, I'm going to right-click and I'm going to import the model from the file. And this is going to be that .vdp file that I just created for my seating structure. So I select this stair file, I click Open, I click OK, and now these stairs are automatically available to me within my RF-WIND tunnel. Now we obviously need to change the orientation of this structure quite a bit. We certainly don't want the seating to be oriented only half covered. So we can do so by either double clicking on the stairs. We can change the position here according to the X, Y, and Z or the rotation. What I like to do is just to simply right click. We can also manipulate it if we're not so concerned with the exact location here. So I will essentially rotate it. I can also move it to the left or the right here. I can move it front or back, all graphically within the model. Maybe we take a look at the orientation from the X direction just to further move this structure a little bit over to the center. Okay, so now you can see the stair structure oriented underneath my tent. Ultimately, we'd want to start this calculation results within RWIND simulation. Again, it does take just a minute to solve. So what I have went ahead and done is solved the model already, and we'll jump to this. We're going to see pressures now once the calculation is finished, even on our stair structure. But again, we're not so interested with this. We're more so interested in the pressures and how they're affected on the actual tent structure itself. And what we might use is the streamlines again. So we previously covered the streamlines. Essentially, these are going to show the direction and the magnitude of the wind, but now they're also going to consider this additional body underneath the tent canopy. We can edit our streamline settings, and I can use these modifiers here to kind of change the geometry of my streamline box, and we'll set this to something pretty small. I also want to move it over to the center of my structure. Maybe we change the orientation here in the X direction again. We can also change the height of these streamlines as well. So when I click OK, I'm only going to see the streamlines passing right through the center of this structure, through this rectangular box. And the easiest way to probably see this is if we change the orientation here according to the Y direction. So we can see exactly what the wind is doing. It's hitting this stair structure here, passing up over the top and then passing out through the exterior of the tent. Notice the extreme change in velocity here. So we could probably deduce that someone sitting at the top of this stairs or this stadium type seating is going to experience much higher velocity than somebody sitting at the bottom. And we can turn this back into the Y direction. What also is powerful is let's turn on our streamline animation. So for this, I've set this to particles to follow those streamlines, and you can see them hitting the stair structure and then kind of passing out through the top. Now, additionally, we have the wind, of course, just kind of passing through the top here as well. So pretty powerful, again, in just understanding the influence of additional adjacent structures, or in this case, it was underneath our structure, and how the wind loads will be affected. Now, ultimately, like I said last time, the surface pressure is what's going to be most important to us. We can export this information back out to RFEM, and maybe we have 3 additional load cases for wind loads to consider the addition of this seating structure below it. So quite powerful, again, in how we can use RWIND simulation integrated within RFEM for wind design. So I will conclude today's webinar and jump back to the PowerPoint here. You can always visit our website at dlubal.com for more information about RFEM, RWIND Simulation, any of these add-on modules. We also have our web shop, which you can see all of the pricing information. I encourage everyone to follow us on our social media sites. For example, you heard me mention our YouTube channel. This has all of our previously recorded webinars, short videos that you can watch at your own leisure. Several of our other social media sites will just kind of announce maybe some new technical articles, frequently asked questions, any online events and conferences we'll be holding in the coming months. If you have any questions about today's presentation or anything else, feel free to contact us in our Philadelphia office at info-us@dlubal.com. You can also call us at 267-702-2815. Again, this is our Philadelphia office, so feel free to contact us here. We will have many more upcoming webinars. You can register on our website at dlubal.com under support and learning and webinars. As most of you know, I send out a couple reminder emails before these will take place, so feel free to keep signing up through the email directly. I also want to mention that we have 5 on-demand webinars that are available through April 30th for PDH credit. So we know with a lot of conferences that were recently canceled, engineers rely heavily on these for PDH credit. So we wanted to supply 5 previously recorded webinars that you can, again, watch at your own leisure. You take a quick 5-question quiz and the PDH certificate will automatically be emailed to you. These are available through April 30th, so you can earn up to 5 PDH credits. Now, this is not posted on our website, so if you have any questions or are looking for the registration for that, if you didn't previously receive it, send us an email here at the info-us@dlubal.com. As far as today, PDH certificates will automatically be emailed to all participants who were here for the full presentation. That is a requirement from the states where we are pre-approved providers. If you yourself did not register with your own name and your own email, let's say you watched under a colleague's registration, you will need to request a PDH certificate, again at the email shown here, info-us@dlubal.com. And with that said, I want to thank everyone for attending today's webinar, and as always, we hope to see you at the next presentation. Thank you.